Okay, before we can go much further in this unit, we really need to take some time to talk about the underlying laws that dictate everything we've been doing in thermodynamics. To do that, we're first going to start with the zeroth law of thermodynamics, okay? We call it the zeroth law because it actually kind of came after laws 1, 2, and 3, but being more fundamental means that they actually wanted to identify it as being first, so this is how they did it. So essentially what we're saying in the zeroth law is that you need to have, if you have three objects that are in contact with each other, so A is in contact with C, C is in contact with B. If A and C are in thermal equilibrium with each other, now be very careful, thermal equilibrium is very specific. It means they have the same temperature, okay? Does not mean they have the same amount of energy, okay? It means they have the same temperature. Because if object A is really tiny and object C is very big, having different masses would give them different amounts of overall energy. But if they're touching each other, A and C will eventually come to the same amount of energy, okay? It's no different than taking a can of pop out of the refrigerator and letting it sit on your house. Eventually that can of pop is going to warm up until it's room temperature, okay? And what they're saying is because the can of pop is sitting on the countertop and the pop are both at the same temperature. And the glass of water 3 feet away that's also on the countertop, if you give it enough time, will also be at room temperature. So as long as all three things are in contact with each other and given enough time, they will all reach an equilibrium or be at the same temperature, okay? Be very careful though. We don't want to think that thermal equilibrium is the same amount of energy. We want to make sure it's the same temperature is what they'll all come to, okay? Now, the second part of this thing is actually the first law of thermodynamics. And with that first law of thermodynamics, we're saying what happens now in terms of the energy transfer, okay? So when we have an isolated closed system, meaning that we are able to insulate this and keep control of this. If we have one substance gaining energy, some other substance has to lose the same amount of energy, okay? So we can't gain or lose energy overall. We have to track it completely. So what we're saying is that the energy gained in one part of our system or within our system is actually equal to the energy lost to those surroundings. Okay, if we bring that back to our thermochemical equations, we know that if we have an overall gain in potential energy of our bonds, that means that the surroundings or the kinetic energy that was available had to lose that same amount of energy, okay? So we didn't really say they had to be equal before, but now we're saying that they had to be actually equal to each other, so you can't lose any energy. Now, technically, there's a problem with this, okay? So technically, if you gain energy, it can't equal lost energy because they have opposite signs, okay? So the way we fix that is we actually put another negative symbol into one side of our equation. Okay, it's probably easier to identify this by doing a little bit of math, all right? So let's say we had a system where the system gained 150 joules of energy, okay? For it to gain that energy, something else has to lose 150 joules of energy, okay? So for example, maybe we ran a chemical reaction that was endothermic and had to gain 150 joules of energy. So the surroundings had to lose 150 joules of energy, of kinetic energy, for example, okay? The problem is if you're losing energy in comparison to gaining, a positive 150 gain is not equal to a negative 150. They're opposites of each other, okay? So mathematically, the fix for this is our first law of thermodynamics actually accounts for the fact it's equal but opposite of our effect. So instead of saying we have 150 joules positive trying to equal a negative value in terms of our math, instead we just add another negative sign. So a positive 150 joules does equal the opposite of a negative 150 joules, okay? This becomes important because as we start to put more and more numbers in our stuff, if we don't add this extra negative sign, we're going to have in effect where we're going to be doubling our values versus canceling each other out, okay? So it's kind of how it works. From this, we now can start setting things equal to each other and doing more mathematical relationships with this gain and loss of energies. Now, the last part of our things we're going to talk about is actually the second law of thermodynamics. We won't talk about the third in this unit. And the second law of thermodynamics is actually pretty large. It had lots of pieces to it. We're only going to talk about one component of that, which is heat flow. So we're only going to talk about what happens, how heat flows. And to do that, I'm actually going to back up and come in and do the animation again. So if you have something at low temperature and something at high temp and they touch each other, okay, or come into contact or in the same vessel, the thing at high temp is going to allow energy to flow into whatever is at lower temperature. That heat flow will continue until they reach thermal equilibrium, same temperature. Not same amount of energy, same temperature, okay? Here we go again. Two things at different temperatures are put together. We have a flow from hot to cold, and that's how heat has to flow, okay? In reality, in our day-to-day lives, we use the term cold, but in the world of thermodynamics, there is no such thing as cold, okay? It's just different amounts of heat energy. So things that are hot have more heat energy. Things that we would call cold have less heat energy. So when you put the two things together, we always have a flow of the higher energy or the hotter thing of energy into the lower temperature thing, okay? As a result, eventually they'll come to thermal equilibrium. And once they're in thermal equilibrium, they now, we say, have the same amount of temperature, okay? We're going to put all three of these kind of components together to start talking about these relationships between how our values at change temperature can equal our thermochemical equation values from our previous module. But for now, we're going to stop the video and we'll go from there.